Okay, good morning, everybody. Let's get started. Let me share my screen. Everybody, could you see my screen?
Yeah.
Yes, sir.
Yes.
Okay, great. Yeah. You see, today we will start the new chapter, which is three-phase induction motor. And this is very, very important motor. This motor is extensively used in industries. Like about 80% motors that are used in industries are the induction motor, and then that is the three-phase type. So therefore, today we will be looking at its operating principle, and on concept called rotating magnetic field, we will be looking that. Another important concept, it is called the slip. What is the slip of the induction motor, that we will be looking, and then construction of rotor, and then magnitude of rotating magnetic field, followed by some numerical example. So moving forward. So first of all, you see everybody on the top, I have written induction motor, rotating transformer. That's pretty interesting that induction motor is called rotating transformer. So meaning that, sorry, okay. You all know that transformer is the static device, and transformer had the primary coil and secondary coil, and there was no direct connection between primary and secondary. So similar to transformer, induction motor has also the primary coil and secondary coil. I mean, which we call stator and then the rotor. We don't always call the primary and secondary, but induction motor has two coils, primary coil, secondary coil, similar to transformer. But induction motor will rotate. It has a shaft. That shaft will rotate. Accordingly, induction motor is called rotating transformer. I mean, this is pretty interesting. This means that the working principle is the same as to the transformer. And then you see, I have written here that induction motors are extensively used in industries. What are the reasons? Due to its low cost, simple and rugged construction, minimal maintenance requirements, and good operating characteristics. So these are the main feature or the main characteristics that induction motors are mostly used in industries. Now, as I said that it's a rotating transformer, this means it has primary and secondary. So the primary is called the stator. I mean, soon I am taking you to that whiteboard and drawing a picture. Primary is called stator. It has three-phase windings. And secondary is called the rotor. And that rotor has two types. One is called wound type. It has three-phase windings similar to the stator windings. So, and then squirrel cage type, it has conducting bars. I am coming this time later, but just at this point, everybody just remember these two terms, stator, rotor. Stator is analogous to the primary coil, rotor is analogous to the secondary coil of the transformer. Now, let you take to that whiteboard, just a moment. Okay, so everybody say, this is on body, which is called stator. So this body is called the stator. This body is stator. And that stator has three-phase coil. This is A phase, then 120-degree apart. B phase, then another 120-degree apart, C phase. So therefore, this is C phase, this was A phase, and then this was B phase. So A phase, B phase, C phase. So then everybody see that induction motor has the primary, which is called the stator, and that has three sets of coil, A phase, B phase, C phase. Now there is another body, another circular body. This body is called the rotor. So this means this is the secondary, similar to the transformer. And again, it has another three sets of coil. For example, this is A phase, this is B phase, and then this is C phase. So therefore, both stator and rotor have similar structure, both have three-phase coils. And because this is induction motor, we are discussing induction motor. This is the induction motor. So consequently, it has a shaft. The shaft is attached to the rotor body. This is the shaft. Shaft is connected to the rotor body. This is the shaft. Okay. So now everybody see that how it works. I mean, this is very important. Because this is motor, so what we have to do? We have to apply three-phase voltage. So that's why you see current direction this way. This means this is IA, and then this is IB, and then this is IC. So meaning that this side is your line or this side is your grid side. From the grid, you are applying three-phase voltage to the stator coils. So initially, everybody remember, this is induction motor, but initially shaft is not rotating. This is not moving. Initially it is static at stationary position. We have to make it rotate. That's why at first we have to apply three-phase voltage, in other words, three-phase currents. Now everybody see that this current is entering into this coil, this current is entering into this coil, and then IC current is entering this coil. So therefore, now you tell me what is the consequence of applying current to a coil. For example, you have a coil here. This is a coil, and you are applying the current here. So what is the consequence? What will be the effect of applying current to a coil? So it will produce flux. So you all know that. It will produce flux. It will create a magnetic field. That's the result, or that's the consequence. So therefore, similarly, once you apply three sets of coil, therefore there will be flux here. For example, this is phi A, that flux. Similarly, there will be flux here, which is which is phi B. Similarly, there will be flux here, which is phi C. This means there will be three sides of magnetic field. Now, if you combine them like phi A plus phi B plus phi C, their combined effect will be a resulting magnetic field that is rotating. Actually, it is rotating in that way. You see, this is the combined. So I gave the name like phi S, where phi S refers to stator flux. Let's give its name. This is called the stator flux. Stator flux or field. So therefore, everybody see, after applying three sets of current, then they are producing three sets of magnetic field in their respective coils, but then there is a resultant magnetic field. And this resultant, which I have designated phi S, stator flux or field, that is revolving, that is properly rotating, the combined one. And that rotational speed, what is the speed of that rotation? This is the equation. Ns 120 F over phi. So therefore, F is the frequency. So you all know that F is that frequency, and that phi is the number of pole. Phi is the number of pole, and Ns is that speed. This is the speed, and it is called the synchronous speed actually. It is called the synchronous speed. This ns, synchronous speed, and this is expressed in terms of RPM, or revolution per minute. So therefore, everybody say that ns, synchronous speed, which I have defined 120 F over P, where F is the frequency. Which frequency? Applied voltage or applied current frequency. And that this is the pole number phi. So what is that pole number? Because that rotating magnetic field is produced, you all know, a rotating magnetic field means it has that north pole and it has the south pole. It has the north pole and south pole, and not just only one set. There can be multiple set, multiple north pole, south pole. It depends on how we design the coil, how we place the coil. Therefore, keep in mind this number of pole, that phi, there are no physical magnetic poles. No physical poles. These are the internal pole. You can't see these poles. These are being developed because of this magnetic field. So therefore, I mean, in summary, when I said that because of the application of three-phase current, there is a resultant magnetic field, and that resultant magnetic field, I am telling stator flux or field, that is rotating at this speed. Keep in mind, this speed is not the shaft speed. Everybody, I mean, don't be confused or mixed up. This speed is not the shaft speed. Still, the shaft has not rotated. Still, the motor has not started moving. What I am telling that this speed is 120 F over P RPM. This is the speed of the rotating magnetic field. Okay, so now everybody say, you got a rotating magnetic field, and these coils, the stator three sets of coil, this coil, this coil, this coil, they are fixed. They are fixed. So what will happen, and even initially these three sets of coil, because rotor is not moving, because shaft is not moving, initially they are fixed. So what will happen, this magnetic field will produce voltage or will induce voltage on these three sets of coil. Let's designate, for example, this is A prime, this is B prime, and this is C prime. So therefore, this rotating magnetic field, or in other words, stator flux or field, will produce voltage on the rotor three sets of coil. And again, if it is closed circuit, then current will flow through these three sets. And once again, what is the consequence of flowing current through three sets of coil? There will be again another set of flux. Let's designate this is phi r. Phi r. Phi r refers to rotor magnetic field. Now you have original that stator flux rotating magnetic field, which was revolving at that speed. Now you got another set of magnetic field, which is phi r. Now there will be interaction between this phi s and phi r. I mean, there will be interaction between phi s and then phi r, because there are two sets of flux. Because of their interaction, now torque will produce, and this shaft will start rotating. For example, at a certain speed, I will designate NR. NR refers to rotor speed. rotary speed. So therefore everybody say, this is the actual motor speed or shaft speed, which I am defining by the symbol N subscript R, because this is rotary speed. But here it was Ns synchronous speed, or this was the stator flux speed. So therefore there are two speed. I mean, don't mix up. Nr is the only shaft speed, or you can say this is the motor speed. Also, you can tell it this is the motor speed. So motor speed and rotary speed is the same, which is the shaft speed. But this is the synchronous speed, is only the stator field speed, which is revolving. So therefore, once again, everybody see what I did, see the sequence. If you are asked that how does an three-phase induction motor moves or operate, so first you have to apply the three sets of voltage in the three sets of coil. In other words, three sets of current. And once you apply three sets of current, then there is a resultant magnetic field, which is revolving at this speed, and which I am telling stator flux or stator magnetic field. And because of that magnetic field, because that is rotating, consequently, voltage will be induced on the rotor coils. Consequently, there will be current flow. And as a result, there will be rotating magnetic field, which is the rotor magnetic field, phi r. This is the phi s, stator field. And now because there are two sets of flux, so there will be interaction between phi s and phi r. And hence torque will be produced and this shaft will start rotating. So therefore, it will have different speed, which is the motor speed or rotary speed. This means that if you have a tachometer, if you measure the speed here, then you will get some number. Now, what will happen, and you see, this is another speed, which is the flux speed. Now, for example, you see, it is defined frequency, for example, frequency is 60 hertz here, sorry. The applied voltage or applied current frequency is 60 hertz. So you all know. And then just assume that your pole number is 2. You see the minimum number of poles should be 2. That is the minimum. At least there should be one north pole and south pole. So therefore look this equation 120, then this is getting 60, like over 2, you will be getting 3600, 3600 RPM, revolution per minute. This is this speed. And now once the motor has started rotating, I mean this rotor speed and motor speed, if you measure this speed, you will get some small number. For example, 3400 or 3500. At least you can say that this speed must be smaller than this speed. In other words, you can say that that inner, I would write here, that inner should be less than this ns. Always there should be difference. If they are equal, then motor cannot run. I mean, soon you will understand. At this point, everybody just hold this on, that ns must be greater than nr. This means magnetic field speed should be greater than the actual shaft speed, which I am telling rotor speed or motor speed. So everybody, could you follow me so far?
Yeah, I could follow. How much greater is the stator speed, the synchronous speed, than the motor speed? So usually
Okay.
a lot greater.
And then no. I kind of, for example, I have shown this on like 200 RPM, or even it could be smaller. So that's why there is a term I will define. Therefore, I mean the good question. there will be a term which is called the slip. It is called the slip. SLIP. Slip is, what is the definition of slip? Slip is that ns minus nr ns minus nr over ns. This is the definition of slip. So therefore, for example, I am answering to your question that what should be, how much should be the difference. So therefore, typically slip is kind of 5% slip value. It is expressed in terms of percent. This means, just a moment, let me delete this one. Okay. So multiplied by 100%. So therefore, this is the slip ns minus nr, the difference divided by the synchronous speed ns and taken as a percentage. Typically, this slip value is 5%. Therefore, for example, if ns value is 3600 rpm, and if you assume slip value 5%, probably it will be close to 3450 or something. So therefore, this will be the difference, like 150 rpm. I mean, or not more than that. So, do you understand?
Yes, thank you.
Yeah. So therefore, for every mode, I mean, soon today, I mean, at the end, we will be solving a numerical problem. Most probably, we will be using the slip percentage, 5%. That time, you will be noticing that around this number, the actual SAP speed, there must be some difference. So this means that everybody, therefore, this is the thing, everybody understand. I mean, when solving the problem, don't mix up two speed. One is ns, n subscript s, other is nr. Nr is the actual motor speed or the rotor speed or the shaft speed. Three terms can be used: shaft speed, rotor speed, motor speed. All are this one. Only this one is the synchronous speed, which is the magnetic field speed, which at the beginning when you are applying three sets of voltage and it is producing a rotating magnetic field. And keep in mind, there are no physical magnetic poles. There are no. Therefore, this pole number in the equation, this is being developed internally, intrinsically. You can't see this one. It depends on pole number is 2, pole number could be 4, pole number could be 6. It depends on the coil arrangement. By changing the coil construction, you can change this number. So therefore, everybody keep in mind this pole number, minimum pole must be 2. You all know that every magnet has at least north pole, south pole, at least 2 pole every magnet. So therefore, minimum pole number should be 2. It can be 4, 6, depending on the motor. And then your frequency, this is the applied frequency. What was the frequency of the applied current or the applied voltage? And you all remember this term. Now everybody concentrate this equation, slip equation. Let me clean up this portion. Everybody concentrate. Okay. Everybody concentrate the slip equation. So what I said, the synchronous speed minus rotor speed. So now think about that ns equal to nr. Ns equal to nr. So what is the meaning of ns equal to nr? This means this magnetic field speed is equal to that speed, shaft speed, this nr speed. So if that is the case, then what will happen? Because shaft is rotating and then the stator flux both are rotating at the same speed, consequently, there will not be any voltage build up on the rotor. Probably you could remember that at the very first class, or I think at the beginning of three-phase circuit chapter, I told you the condition. For example, everybody say, for example, you have a magnet, north pole and south pole, and you have a coil. So how to produce the voltage in this coil? There are two things. Either you have to make it rotate this coil, either you have to rotate this one, keep it fixed, keep this coil fixed, and move this magnet around the coil. Then voltage will build up. Or you move this coil, you move this coil, but keep this fixed. Then the voltage will build up. Now you can move both together. Move this coil, move this magnet and move this coil together. If you move them at the same speed, if you move them at the equal speed, then there will be no voltage produced. At least there should be relative difference in speed. There should be relative speed. Everybody, could you follow me what I am saying?
Yes, sir. If the two are equal, is that only possible in an ideal situation?
No, even though no, even though no. So that's why, I mean, you see initially, what is the sequence? When I applied the voltage, everybody remember, these both coils, both rotor coils, stator coils are fixed, static, nothing moving. Once you applied at the beginning the three-phase voltage, that produced the rotating magnetic field. Because that was moving, I mean, similar to this one. For example, if you move this magnet around this coil, only then voltage will build up. Meaning that there must be relative motion between these two bodies. Either this should move or this should move, or if you move both, if you rotate both, but there should be difference in speed. If you move both at the same speed, there must not be any voltage. That is the principle. That is called the Faraday's law of induction. There should be, there must be difference. That's why here, once you applied the voltage, there was a rotating magnetic field. Consequently, voltage all build up on those rotor coils. And then at the next time, there was another rotor field and there was interaction. But as I said, there should be difference. Because initially this phase was produced, that this rotating magnetic field was built up at the beginning, and this is the dominating. This was the main driving force, this stator magnetic field. And that caused the voltage here and consequently another sets of flux. That's why naturally the speed of this, the rotary speed is lower than this one. Now it might happen that you could make this speed much bigger than this one. For example, I said, you see this condition, NR less than NS. If you make, for example, by force, NR greater than NS, for example, you make this situation. How that is possible? I mean, sorry. How that is possible? For example, you add something here with this shaft was rotating, that is fine with NR speed, but you add something. For example, you added a wind turbine. You added a wind turbine, and that is also rotating. So, and that increased the speed of this shaft. Then it made this condition, NR greater than NS, NR greater than NS. Now, if you make NR greater than NS, then look this equation, slip definition, you will be getting negative value, you see, because this term is larger than this term. So slip will be negative. So if this is the condition, NR greater than NS, then this will not work as a motor. This will start working as a generator. In that case, you will tell this on induction generator. In that case, what will happen? You see my current flow direction will be changed. Rather than taking power from the system or from the grid, you will start providing power to the grid. Because your shaft speed has much greater than the synchronous speed. This means the mechanical side shaft side is dominating than the electrical side. So in that case, it will work as a generator, not motor. Okay, so we are coming that point later. So the question was, I am just trying to explain why there should be difference between these two speed. What is wrong if both are the same? So that is the thing I was explaining you. I was telling you that if you have a coil and if you have a magnet, then if both are static, if nothing move, then no voltage. If both moves but with equal speed, then still no voltage. Therefore, you have to make a relative difference, relative speed. If you think about the physics, relative motion, you have to make the relative motion. Therefore, if you rotate both, then make some difference. Or you just keep on static, fully stop. Either you fix the coil, then move the magnet, or you keep it fixed, you move this coil. In both cases, the voltage will build up. So that's why if you see the slip definition, this is my slip definition. If you make both equal, consequently, what will happen, even though initially motor started rotating, but with some arrangement, you make both equal, what will be the consequence? Next time, there will not be any voltage on the coils because that is not meeting the requirement of voltage induced. There is no relative motion. Consequently, there will not be any rotor magnetic field. So there will be no interaction, no torque, motor will be stopped. So therefore, everybody keep in mind, Ns equal to Nr means motor is stopped. So and at that time, what is the value of the slip? When Ns equal to Nr, what is the value of the slip? According to the equation, slip value is 0, right? Yes. So therefore, slip value 0, meaning that Ns equal to Nr. On the other hand, everybody see, at the beginning of the operation, when the shaft was not rotating, when you applied the voltage, there was three-phase magnetic field. That is fine. This means that in the equation you have Ns, but what was the value of Nr at that time? Nr value was 0 because still the shaft has not started rotating. So Nr value was 0. So what is the value of the slip under that case? So Ns over Ns, slip value is 1. So therefore everybody see that when the slip value is 1, motor is not rotating, shaft is not rotating. When the slip value is 0, at that time also your shaft is not rotating. So this means then when to rotate. So therefore the best thing is that typically when the slip value is kind of 0.5, sorry, when the slip value is 0.5 or the 0.6, around that zone, this motor runs well. So therefore for three-phase induction motor, the best value or optimal value of slip is 0.5 or the 0.6. Around that value, the motor runs well. And at these two extremities, motor is stopped. It does not run. So slip value 1 means motor was fully standing still. There could be, you may apply the voltage, there will be rotating magnetic field, but shaft is not rotating. That is the meaning of the slip 1. And slip 0 means both speed are the equal. Consequently, shaft is not rotating. Therefore, to rotate the shaft, the slip value must be between these two. It should be between 0 and 1. And then as I said, like typically 0.5, 0.6, these values are the optimum for the best operating condition of three-phase induction motor. So far, everybody, could you follow me?
Yep, so far so good.
Yes, great. So I will give you an analogy. Then you will. I want to further explain why. I mean the NR should be less than NS. Let me tell you one analogy. Then you will get fun. Uh, so let me do something, and I will explain you what I'm trying to do. So therefore, like you all have your backyard, right? So and then if you go backyard, and I'm assuming that each of you have some sort of trees at the backyard, and if you collect just a simple leaf, and then if you make, for example, this type of shape, and for example, I think let not this one. Let me redraw. Okay. What I'm saying that if you go your backyard and you just collect a leaf from your tree, and then you make this structure. This structure means I'm doing, like, for example, left side has more length than the left side is larger than the right side. Or you could reverse, you can make right side larger than the left side. What I am saying, you make unequal. And then so you make a hole here, and at the hole you just take a stick, you just put a stick, I mean from the, and if you against the wind, if you just hold this one by your hand, this is the stick, and you made your leaf, so you will notice that it has started rotating. So therefore, because this side is heavier than this one, it will start rotating this way, because this side is heavier than this side. If there is wind at your backyard, then this will start rotating in that way. Never ever it will start from this side. It will start from the heavier side. So that is the meaning it here. Because that ns is greater than this nr, so that's why the direction of rotation will be, the direction of rotation of the motor or the shaft will follow the direction of the magnetic field, because this is the condition that ns should be greater than nr. That's why this motor or the shaft will start following the direction or the movement of the magnetic field. So that's why I made this analogy. Like when I was, elementary school student, I mean, long ago, that time frequently I did this one. So I just went like outside, backyard at my home, and I just took a leaf from a tree, and I made this type of structure. I mean, really I did. And then I put a stick here, and I'm assuming that there is wind, then this will start moving. And then if you start running, this will start move faster and faster. It will spin faster and faster. So everybody, could you follow me what I'm saying? Has anybody ever tried this thing?
I can't say that I have.
So therefore, I mean, everybody, I mean, today you can go to your backyard, you may try, you just take a leaf, a little bit bigger, and you make this shape. I mean, the condition is that one side should be bigger. If you make this side this, and then you make the other side much bigger. For example, in this case, I made the right side much bigger than this one. And in between here, at the connection point, you just take a stick. And then if there is wind, you see that this will start moving in that way. This leaf will start rotating. Exactly, the induction motor follows the same principle. I mean, as I told that when I was elementary student, I frequently did this on, but at that time, I definitely I did not understand, or I could not explain what is the reason that it starts moving in that way. It does not start from the lower side. It must starts moving from the, now, like being an engineer now, and when I read the working principle of induction motor, going to my undergrad study, then I could understand, and I remember my early days, and I did a lot. I mean, several years I did this one. When I was even at the beginning of that junior school, like I did this one frequently. I did, and like I got fun. And if you start running a little bit, then it will move faster if there is enough wind. It's exactly the same principle. So this is coming from the nature. That is the reason your the phi is speed. This means ns must be greater than nr. Okay, so that everybody understood. And then as I told you that for some, I mean, by some arrangement, if you can, sorry, by some arrangement, if you can make this safety speed is greater than this one, this means if you could make this situation NR is greater than NS, then your sleep value is getting negative. You will get negative number. Under that condition, it will start working as a generator, meaning that it will start providing power. And the best example is that wind generator, wind turbine system. In case of wind turbine system, exactly the same configuration inside. Here you just attach a windmill, wind turbine or wind blades. Then your NR will be greater than NS, meaning that your sleep value will be negative. Okay, so with that, everybody now go back to that slide where I was originally. Okay, so I was explaining, and you see the next slide. Actually, I explained all those things here. That rotating magnetic field, speed of rotating magnetic field, this one, 120 F over P, revolution per minute. I mean, today we will solve a numerical problem. That time we can use this equation. And I said sleep speed, Ns minus Nr. I mean, this is the sleep equation. You see, I was explaining you Ns minus Nr over Ns. So Ns minus Nr, this term is called sleep speed, sleep speed. And then, alternatively, you might express in terms of omega or radian per second. When you will be using the symbol NS/Nr, this means this is in RPM, revolution per minute. And if you use these symbols, omega S, omega R, omega S, these are in radian per second. I mean, it does not matter. You will get the same result. But sometimes some problem asks, okay, express these things in terms of radian per second. That time you can use, or still you can use the same equation. You can just convert from radian per second into RPM. So it does not matter. And I have written here, sleep varies between 0 and 1. So this is very important. Like again, in the midterm exam, final exam, or anytime, I will be asking you this question: what is the range of sleep in case of induction motor? Then you will be answering this one. But if it is induction generator, then the sleep value will be negative. Sleep will be negative. That thing I told you. Okay, so moving forward. Now, as you can clearly understand that similar to transformer, it has two parts. The primary is called stator, secondary is called the rotor. So stator is always the same, but rotor has two construction. One is called wound type rotor, other is called squirrel cage type rotor. Squirrel cage and wound rotor. So therefore, like if you see this, I mean, before going much more about this feature, first everybody have a look. Wound rotor. So we are discussing the construction of the rotor circuit. So therefore, again, because this is three-phase system, both stator and rotor coils can be placed either in delta format or Y format, because three-phase circuit. So in this case, for example, this is the example of the delta circuit. You see the stator. So the outer side is the stator, and then inner side is the rotor. And it is called the wound rotor because there are coils. And then it is also the delta. And then there are three terminals. Outside the three terminals, there are external resistors, three sets of, with the help of slip ring and brushes. But see the bottom structure, squirrel cage rotor. You see, this is the structure. You see, this looks like a cage, and you all know the squirrel animal, right? So you might have seen at your again backyard or somewhere. And accordingly, it is called the squirrel cage type. So the feature is that it does not have coils similar to these coils, rotor coils. Rather, it has the conducting bars. These are just the conducting bars. These are the good conductor, but not the coils. And it looks like the form of a cage, a squirrel cage. Accordingly, it is called a squirrel cage type of rotor. So therefore, see the difference here. When it is wound rotor, meaning that it has the coils, because it has the coils and it has 3 terminals, you are able to connect external resistor with the help of slip ring and then brushes. Because this thing is moving, and this thing, you see, because this is in the rotor circuit, therefore these 3 things, slip ring, these are like moving, but then this is static, this is outside. So therefore you need a brush. That black colored thing is kind of contact brush. So therefore this thing is fixed, but these slip rings, these are moving, and then this is just the touching. And consequently, you can connect any external resistor. So therefore, if you can connect any external resistor, and if you can vary these resistance, you can control the speed of this rotor. But in this arrangement, you see, I did not draw anything, because in this case, squirrel cage type, there is no provision, there is no option to connect any external resistor. Consequently, for squirrel cage rotor, you cannot change its speed. So therefore, that is the basic difference, that in case of wound rotor, you can connect external resistor, and hence you can control its speed, because you are controlling the current flow through the coil. Consequently, you are controlling its flux. Accordingly, you can control the torque or speed. Here you don't have any option. So now the question is, when to use this one and when to use this one. That's why now you go back to the previous slides. Now everybody read. Construction of rotor, wound type. It has 3-phase winding similar to stator. It has slip rings that you noticed. External resistors can be connected to the rotor winding through brushes slip ring. It can provide variable speed operation. For example, variable speed wind generator system. Now, wind generator are 2 types. One is called variable speed, and for the squirrel cage, I have written fixed speed. So therefore, when you need a fixed speed wind generator, then that is the squirrel cage type. You have to choose this one, because you cannot control anything externally. There is no such provision or option. But here you can control. Consequently, the best place to use wound type is variable speed wind generator, or in industry, frequently you need variable speed operation. So for industry, you have to use wound rotor type. On the other hand, where you need fixed operation, here just an example of wind generator fixed speed, where you need constant speed operation, then you have to choose squirrel cage. So that's why everybody see I have written. It has no windings similar to the stator. However, it has conducting bars short circuited at both ends by the end rings. So it is talking about this side. Yes. These are just conducting bar. And it has no slip rings, no brushes, so external resistor can't be connected to it, and it provides constant speed operation. So I will be asking you these differences. What is the difference between wound rotor type and squirrel cage type in the upcoming exams? Everybody, could you follow me?
Yes.
Yeah. So in the, sorry?
Squirrel cage fixed speed generator. How? I mean, do you? I guess I'm confused. How do you know that the wind is going to be moving at a constant speed?
Okay. So the good question. So the in case of the fixed speed, wind speed no. So this does not mean that the wind speed is fixed. There are 2 arrangements in case of wind generator. After taking the varying wind speed as the main input, then later on the shaft system, there is some mechanical arrangement in this case that always provides the fixed speed. Therefore, wind speed is varying. At the beginning, it has the varying speed. Later, with the help of some mechanical arrangement, it is called the pitch control of the mechanical system, of the wind system. Speed is made fixed. So therefore, fixed speed wind generator means wind speed is not fixed, rotor shaft speed is fixed with the help of mechanical arrangement. In this case, both rotor shaft speed and then wind speed both are varying. This means the variable speed wind generator is adaptive, is compatible, is flexible with the variability or variation of wind speed. In this case, initially it accepts the varying wind speed, but later inside there is mechanical arrangement, gearbox, and pitch system that makes the shaft speed fixed of the generator. Therefore, when I am saying the fixed speed, this is the like generator part, not the wind speed. In this case, variable speed, this is the shaft speed varying, and it is adaptive, it is compatible with the varying wind speed. That is the difference. Could you follow me?
Okay, thank you.
Yeah. So therefore, fixed speed does not mean the wind speed fixed. I mean, by chance, for a moment, for 1 minute, 2 minute, wind speed can be almost constant, but in real practice, wind speed is never ever fixed. Always there is some sort. Therefore, by the word fixed speed, this does not mean the wind speed fixed. Meaning here is that rotor shaft speed has been made fixed with the help of some arrangement. Okay, so everybody is fine so far. Okay, so therefore moving forward, everybody see here, I think I already discussed, induction generator has negative slip. That thing I told, but I have written two important things. Induction generator provides real power to the grid, but it still draws reactive power from the grid. Induction motor draws both real and reactive powers from the grid. Alexandria, are you on the line? Hello, Alexandria Golden, are you on the line? So, I mean, why I'm saying this, like you have assigned the class project, so your project is very similar to these things. So that's why, and Alexandria and then her group, you please listen carefully. This thing will help you to simulate that induction generator.
Okay,
So,
I'm part of her group, so I can give her that information also. Thank you.
oh, so Mona, you are right in that group. Yes. Okay. So therefore, you listen carefully because your topic is induction generator. So therefore, what I said, induction generator provides real power to the grid, but it still draws reactive power from the grid. And induction motor draws both real and reactive power from the grid. So therefore, see the difference. This means that both induction generator and induction motor, both are drawing reactive power from the grid. You see, it still draws reactive power. And because this is induction generator, it is sending or it is providing reactive power to the grid. And because this is motor, it is drawing real power also from the grid. Therefore, because this is motor, definitely it is taking both real and reactive power from the grid. Even though it is generator, although it is delivering real power to the grid, but still it is taking reactive power from the grid. That's the question, that why it is still takes or why it is still needed to take reactive power from the grid. So I like to explain this thing, and that will help you a lot. So 1 second, let me go back there. Okay, let me clean up this thing 1 second, and then let me redraw so then you can get. So therefore, like I am drawing that briefly so that then So what I said that we explained, just I want to show you. And then you assume that there is shaft. We will not explain this thing, we already explained. What I am saying that when it is motor, we are applying power or we are applying the voltage. Then everybody see, definitely the direction of my current and voltage, everything is from the grid towards the motor. Let's say this portion is grid. Right side is the grid portion. And this side is the motor portion, motor or generator. So from the grid power is going. So because I was emphasizing real power, reactive power, the P symbol is used to indicate real power. So therefore both P and Q. So Q is the reactive power and P is the real power. So therefore that will be the direction for the motor operation. This means both P and Q have this direction from grid to the motor. When it is working as a generator, for example, I assume that somehow I made this speed much greater than this, the synchronous speed that I'll be getting, meaning that the sleep value is your negative value. So under that condition, it is generator. At that time, see, the P direction will be this. This will be the direction of feed. I mean, from the generator to the grid, P direction. But still, the Q direction will be this. That thing I am telling. So therefore, in other words, let me draw like this is P direction. This is Q direction. Therefore, everybody, you note down in your note, both P and Q direction, the left side, meaning that from the grid to the motor side, when it is working as a motor, when it is working as an induction motor. But see this one, when it is working as a generator, at the generator mode, P direction is right side from the generator to the grid, but still Q direction is the same. So therefore, see the difference? Both motor and generator mode, Q has the same direction from the grid to the machine, but in this case, P direction is this, and in this case, P direction is this. So now the thing is that is the question like I am asking, and then for Mona and then Alexandria, your group, you have to understand this thing, why the Q direction is always here. So what was the function of sending the power, or what is the meaning of the sending, or why do you need to send the power in this direction? To produce that rotating magnetic field. Everybody remember initially I was telling you that once you apply the three-phase current and then voltage or power, then rotating magnetic field is produced. To produce that rotating field, you must need to send the reactive power. And why I am telling the reactive power? Because these coils, these three set coils are basically the inductor. This is LA, this is B phase LB, and this is LC. These three sets coil that is placed on the stator are nothing but the coil. Inductor, mainly they have the inductor. And if it is mainly the inductor based, definitely that is drawing the reactive power. That is the meaning why I am emphasizing the reactive power. So because naturally, it is naturally taking reactive power, being the fact that they are nothing but the coils. They have only the L. They don't have any capacitor. They have very little resistance. At least they don't have any capacitor. They are fully made of the only inductors. So that's why it draws the reactive power. Now, if there would be any physical magnetic poles, if there would be any physical magnetic poles, then you did not need to send reactive power. Because there is no physical magnetic poles in induction motor, you must create the magnetic field with the help of delivering or sending the reactive power to the system. So that is the necessity of delivering reactive power to the induction motor. Now see the consequence. Now everybody say, What is the consequence of providing reactive power to a coil? For example, we have a coil, just think about any set, and we are injecting reactive power. So what will be the consequence of sending the reactive power to a system? Like what we have learned in the previous chapter, the first chapter, three-phase circuit. If you send much more reactive power, then the power factor will be low. Power factor will be low. So therefore, because this is coil, because these are coils, once you are sending the reactive power factor is getting low naturally, low lagging power factor. And what is the, what is the consequence of having low lagging power factor? The consequence is that there will be some voltage drop at the terminals. Voltage will go down as there will be much more loss in the system. That is the consequence. But then I said that you must need the reactive power. You must send the reactive power to produce magnetization, to produce the magnetic field. But then what is the consequence? What is the adverse impact? Adverse impact is that power factor will be low lagging. And what is the consequence of that? There will be voltage drop. So then how to handle that situation? That's why what you need to do in case of this type of arrangement, you must need to connect some sort of capacitor. Sorry, you must need to connect some capacitor here. Yes, this is one capacitor. At this phase also, at this phase also you connect the capacitor, and then similarly here also you connect capacitor. You make them grounding. So therefore, what is the benefit of putting capacitor here? They will improve the power factor. That we have learned in three-phase circuit chapter. So we can put the capacitor to improve the power factor, to improve the voltage. It will support the voltage. It will not allow the voltage to go down. So you can prevent voltage drop. That's why in case of induction generator, always there is capacitor connected at the terminal. Everybody, could you follow me?
Yes.
Yeah. So that is, therefore those things you see, I have written down in the slide. Let me now go back there. Okay, everybody see this thing, this arrangement. Sorry, everybody see application of induction generator. So you need not to be worried about this system. I am just showing an like real grid model, including induction generator. For example, for this system, you have a synchronous generator. The generator which always operates at constant speed. And this is the transformer symbol, delta Y connected. It is sending power to the grid. And then this is the wind generator example. Wind generator is based on IG that we are right now studying. IG means induction generator. And then there was delta Y connected transformer. They are providing power. But see this capacitor, just now I explained this thing. You must need to connect a capacitor at the terminal. Therefore, everybody just concentrate this portion. If you have an induction generator, then you must need a capacitor. And that thing everybody see, the last bullet I have written, a capacitor is connected at the terminal of the induction generator to maintain the unity power factor at the steady state condition, rated power and voltage condition. So meaning that when the system is running at rated power and voltage, rated power means what is its capacity, what is its allotted value power, and what is its allotted voltage. Just take an example, 220 volt or 120 volt, whatever. At steady state condition means during normal running condition, there is no fault, no short circuit, nothing happened. During normal condition, you must need to connect a capacitor here. That is the thing. So a capacitor is mandatory. So to maintain the unity power factor so that you can maintain rated power and rated voltage. Without this capacitor, here you cannot maintain the voltage. Voltage will go down. And if the voltage go down, even though you connect transformer, so it cannot match, it cannot synchronize with other system, with other generator which are already connected at the grid. So the condition is that you can connect multiple generator at the grid provided that they are equally, they have the same voltage, they are sending the same voltage, they are connected to the same voltage, same frequency system. So that's why here you must maintain a steady or constant voltage here. To do that, you must need a capacitor. That is the reason. So therefore, that groove, like your project, is very similar to this one. You need a capacitor and you have to connect it. Now, for example, there is some sort of fault, some sort of unbalanced or short circuit at this side, then this capacitor is not enough. This capacitor is not enough. You have to put some control mesh, maybe other capacitor or other power factor improvement means. I mean, those are the different. At this point, just keep in mind, everybody, for normal operation, for steady state operation of induction generator, a capacitor is needed to be connected at the terminal. And I will be asking you this question, why do you need this one? Just exactly you will be answering this thing. To maintain or to improve the power factor, to make it unity, so that you can maintain rated voltage and the rated power. That's the thing. Now, moving forward, so here I have written couple of things, you see, that stator voltage, rotor voltage at standstill. Standstill means motor is not running, or rotor is not moving. Everybody keep in mind, the meaning of the word standstill condition means you may apply the voltage on the stator, but shaft is not rotating. In other words, motor is not rotating. It's called the standstill condition. Under that condition, I have written down the stator voltage, rotor voltage equation, E1 and E2. Can you see, like, this equation is similar to transformer induced voltage equation. You see, today at the beginning, I started talking by telling that induction motor is called a rotating transformer. Rotating transformer, meaning that a transformer has primary, secondary. Here, induction motor has stator, rotor. Similar thing. Stator refers to primary, rotor refers to secondary. That's why look their equation. It is very similar to transformer. 4.445 F N. N was the number of turn. In this case, N2 is the number of turn. There is one new factor like K omega, that is called the winding factor. This is only the new term. Because this is motor will rotate and it will have a windage loss. That's why one factor is added here. It is called winding factor. And typically this KW1 or KW2 is pretty much the same. But see the equation, only difference is it is N1, its number of turns, N2 is its number of turns. But everybody see the frequency, F1, F1. In both cases, I have used the same frequency. So because I am discussing the voltage induced at standstill condition, meaning that when the motor has not started rotating, until motor has started rotating, the frequency is the same, both stator applied voltage and the rotor voltage. And this F1 is actually odd voltage was applied. Odd voltage is available at the system, at the grid level. Now, then what I have written, everybody see, under running condition of motor, once motor has started running or rotating, a rotor frequency F2 S multiplied by F. This S is the slip. So this means that once motor has started rotating, because there is difference in speed, consequently rotor frequency will change. What will be the frequency? S multiplied by the original frequency, stator frequency. So, and then we already defined S. Accordingly, you see the rotor voltage equation that will be changed. It will be SE2. This means here you have to multiply one term, which is the S. Now, how these things comes, you see that the slip term, let me take you to that whiteboard once again. Okay. Okay, so therefore today, you know that at the beginning I wrote this equation NS 120 F over P. Now let's designate this F by the symbol F1. F1 refers to the stator frequency. Therefore from here, or you could write this thing. This means F1 is that PNS over 120, right? I just derived from here. F1 is PNS over 120 and F1 is the stator frequency. Now, what I am saying that when the motor has started rotating, I mean under running condition, what I am telling that the rotor frequency will be changed. It is no more F1. Rotor will have a different frequency, which is F2. So therefore, why it will be changed? Because there is difference in speed, which is that slip speed, ns minus nr, which is called the slip speed. So you remember before we were discussing which is called the slip speed, ns minus nr. So what you can do here, that F2 will be proportionate to that number, ns minus nr, which is that slip speed. So therefore, when this is true, under running condition. So we are just guessing that rotor will have a different frequency than the stator frequency, and which is proportionate to this. Now everybody see, if I write down the slip equation, so therefore your slip equation was that ns minus nr over ns. So this means that this ns minus nr you can replace by s multiplied by ns, you see. So therefore, instead of this one, you can say that this F2 is proportionate to s into ns. I can say s into ns. Now, I want to omit this proportionality sign. I want to use the equal sign. Like I want to write F2 is F2 equal to, then I need a constant here, which is P over 120. That I assume that proportionality factor is P over 120. And then this SNS. Therefore now everybody see what is the definition F1? F1 is phi ns over 120. You see here, phi ns over 120. So ultimately what you can say, that F2 frequency is, this is this S, and then phi ns over 120 is this one, F1. So what result I got? F2 is SF1. So I got the new conclusion, meaning that under running condition, when the shaft has started rotating or motor is running, its frequency will be S multiplied by F1, meaning that what was the stator frequency or the supply frequency from the grid, that should be multiplied by the slip. Accordingly, it is sometimes called the rotor frequency or the slip frequency. Everybody, could you follow me what I am discussing?
Yep,
Yes.
sure can.
So therefore, keep in mind that under standstill condition, frequency is the same, which was the original. Once motor has started rotating, stator frequency is still the same, this one, but rotor frequency has changed. You have to multiply by slip. Therefore, you see, in case of induction machine, motor generator, everything is related with this one, with the slip. Slip is the main governing factor. Slip is the main governing factor. Just keep in mind. So now then, moving forward. Yes, everybody now see? That is the conclusion. Under running condition of rotor frequency F2. Therefore, I mean, from today you will be remembering this equation. You will need this one to solve numerical problem. So consequently, now here you see, under standstill condition, both voltage, stator rotor voltage has the same frequency, F1, F1. I mean, N1, N2 are the turn ratio, that is different, number of turns. These are the winding factor, that is different, but frequency was the same. But what I have written, under running condition of motor, rotor voltage here is S multiplied by E2, because I am replacing this one. It is no more F1, it will be F2, and which is S multiplied by F1. This means S multiplied by E2, where E2 is your standstill voltage, rotor voltage, multiplied by the slip. That will be the rotor voltage under running condition or during rotation. So now with the help of these and then the slip equation, we will just look on numerical problem. I mean, it will just take 1 minute or 2 minutes, then we will be done today. Everybody read this problem. A 3-phase 480 volt, 25 horsepower, 60 hertz, 2-pole induction motor has a full load slip of 5%. Then determine the following. So you see how it is expressed. 480 volt, 3-phase. Everybody keep in mind, this rating, definitely this is the RMS value and this is the line to line voltage. Unless otherwise stated, unless problems say this is the phase to neutral or phase voltage, by default, everybody will assume that this is the line to line voltage. This is the standard practice, standard rule to express the rating of the induction motor. And see horsepower. If it is motor, typically its ratings is expressed in terms of horsepower. And probably you all know on horsepower is 746 watt, 746 watt. This is the supply frequency and pole number is 2. Then determine what is the slip frequency. Okay, so the first question is slip frequency means this one. F2 is S multiplied by F1. Exactly the first question. This means slip value is given 5%, 0.05 multiplied by 60. That is the answer for this one. What is the synchronous speed? That equation we learned in as 120 F over P. What is the rotor speed? Rotor speed means NR. And what is the shaft torque? So now in next slide, I have solved it for you. So everybody see, and then you are ready to go. I mean, we will be done. So everybody see what I am doing. Okay, the slip value was 5%. So first question was slip frequency F2, SF1. Slip value is 0.05 from here. F1 was 60 hertz. So I got 3 hertz. See the difference? Rotor frequency is just 3 hertz because there is difference in speed. What does the question be? Synchronous speed, NS, 120 F over P. F is that 60 hertz. In this equation, this frequency is not this one. Synchronous speed always at the stator side, never ever for the rotor. Keep in mind, synchronous speed always refers to only stator. So always you have to use the, what was the actual frequency, supply voltage frequency, which was 60 hertz. Pole number was 2. I got this one. Then the question was, you see, here the question was find out the rotary speed. Question was synchronous speed, but this is rotary speed. Consequently, this means in this equation, that is the NR. So you see, what is the slip definition? Slip NS minus NR over NS. Slip value is this one that was given initially. And then NS, I just calculated in part B, 3600. I have to find out NR. That is the shaft speed, rotary speed. You see, after manipulation, I got NR value is, you see, 3420 RPM. Therefore, you see, today someone asked me, what should be the difference? You see the difference? Synchronous speed was 3600, but what result you got? Actual shaft speed, rotary speed, 3420. 180 RPM is difference. Because there is a slip. It depends on the slip. How much? If it is 3%, then one number. If it is 8%, then different number. So in this case, this is. What was the last question? Last question was find out the shaft torque. So this is the tau symbol, torque symbol. So what is the, you all know from the physics probably. So the shaft torque tau is power over omega in Newton meter. This power is in watt and this omega is in radian per second. So you know, I have written 1 horsepower, 746 watt, this one. So therefore, it was 25 horsepower. See the problem? 3-phase 25 horsepower induction motor. So you have to convert this one into watt. So I am doing this one, 25 multiplied by this. Omega was the rotary speed in this equation, but this is in radian per second. But I calculated rotary speed in RPM. So I have to convert this one into radian per second. So everybody say what I am doing, this number multiplied by 25 over 60. Then that is converting from RPM into radian per second. I got 358.14. I just plugged in there. So 52.07 Newton meter. This is the result. Everybody, could you follow me?
Yes, sir.
Yeah. So therefore, this is not difficult. So once again, you see these slides and then the video and then this calculation. So you will be fine. So in that way, in next class, we will be solving some different other problem, a bit complicated problem and equivalent circuit and much more discussion on this induction motor. And everybody, like your two experiment number 3 and experiment number 4. So I believe if you now just see the experimental description that I have uploaded for 3 and 4 even, right now you are able to understand just based on today's class, experiment 3 and 4. But definitely before that, you will be doing number 1 and number 2, 3-phase system and then transformer. But what I am talking like lab number 3 and 4, right now you are able to you are ready to do if you properly understand this class that I'm saying. Okay, so with that, I will stop sharing. So does anybody have any questions, comments?
I don't have any about this lecture, and we're out of time anyway. But I guess at the beginning of next class, can you give us some hints to number 5 on the homework?